Hello, I'm Eugene Xin, and will introduce our research paper ITAD, Integrative Tensor-based Anomaly Detection System for Reducing False Positives of Satellite Systems. Detecting anomalies for a satellite system is critical, since development and maintenance costs are very high. Especially false positives can be costly. Anomaly detection in a satellite system is very challenging, because satellite data is huge high-dimensional dataset without labels. Also, anomalies are caused by complex system interactions from various factors. In our research, we propose an integrative tensor-based anomaly detection ITAD framework to detect anomalies in a satellite system with the goal of minimizing false positives. We collect 88 types of different telemetries with more than 43,000 telemetry samples from COMSAT to satellite operated by KARI for 10 months. KARI is Korea Aerospace Research Institute. COMSAT-2 is one of national monitoring satellite. These telemetries are categorized into 7 subsystems based on their characteristics. COMSAT-2 transmits the satellite health monitoring sensor data to Earth in a hexadata format. First, we convert this data into decimal values. Next, we do the interpolation. A satellite consists of a lot of models and sensors. We have more data for certain telemetries and less for other types of telemetries, since many data are measured at different time interval. Therefore, for each timestamps in time series, we have many missing values. To address it, we apply the linear interpolation. After the interpolation, the timestamp is recorded every second. However, most of the values remain constant for some period. Therefore, we compress several timestamps into a single row. For this, we extract 8 features at every 10 minutes using a different statistical method. Then, we finally obtain the feature vector consisting of 8 features. It reduces the data size drastically without losing information. Now we introduce our method, ITAD, using a pipeline. As mentioned in the previous slide, first we decoded the hexadata into decimal form and populated the missing values using a linear interpolation and normalized the data between 0 and 1. Next, we extracted 8 features at every 10 minutes and obtained a vector as a final data form. Finally, we are ready to construct a tensor and decompose it. Here, we construct a third-order telemetry tensor consisting of time by feature vector by telemetry as shown in step E. And we have 7 tensors for 7 subsystems. Next, we decompose these tensors using the CP decomposition as shown in equation below. After CP decomposition, we obtain 3 component matrices A, B, and C, as described in figure step F. The component matrix A consists of time to factor, and B represents the factor to feature vector, and C captures the telemetry to factor. To find the optimal solution of the CP decomposition, we utilize the ALS updating method, which iteratively optimizes the solution. Given a third-order tensor, ALS first fixes B and C to obtain the solution for A. Then it fixes A and C to find B, and lastly fixes A and B to solve for C. Updating will be stopped when the iteration reaches 100 or when the convergence tolerance is less than 10 to the minus 8 in this experiment. In this decomposition step, we must decide the optimal size of rank R. We select an optimal rank at the point when the reconstruction error is small enough. Reconstruction error is the difference between the original tensor X and the approximate tensor X prime. X prime is reconstructed with the component matrices A, B, and C. The smaller the reconstruction error, the closer the approximated tensor is to the original tensor. We choose the smallest r by increasing the r from 2 until the reconstruction error goes under 10%, as shown in the graph in the middle. It indicates that the approximated tensor can represent more than 90% of the original tensor. In satellite systems, normal telemetry data might exhibit certain repeating patterns, as many satellite commanding sequences are similar to one another during nominal operation. So, we apply a k-means clustering method for the component matrix A. Then the normal behavior of the satellite would belong to one of the clusters, and the abnormal behavior would not belong to any of the clusters. The reason why we use the component matrix A is that our goal is to detect anomaly points along time, and the component matrix A represents the comprehensive characteristics of all telemetries at each time instance across different subsystems. Clustering is applied row-wise since the time information and the component matrix A is represented as rows. We use silhouette analysis to determine an optimum K. Next, we calculate the anomaly score. If a time sample is normal, it might belong to one of the clusters we constructed from the previous step. On the other hand, if a time sample is anomalous, then it would exhibit distinguishable patterns from those of normal samples and not belong to any cluster. To quantify this, we calculate the Euclidean distance between the value of each telemetry sample and the center of the clustering it belongs. A closer Euclidean distance means that a value is similar to a normal value, and the longer distance indicates that the value is far different from the normal values. To derive anomalies from anomaly scores, a threshold needs to be set. However, static thresholding cannot adapt to various changing conditions and can produce too many false positives. So we employ a data-driven dynamic thresholding method where the threshold value can be dynamically adjusted and adapt to varying contexts. We decide an anomaly is detected when the anomaly score is over and multiply sigma apart from the mu. Mu is the mean, and sigma is the standard deviation of the data in the time window W. M is the coefficient parameter. This measures how far the sample point is away from the mean within the window. Through this, we finally can find the anomalies. We compared our approach with 4 other well-known anomaly detection baselines developed for satellite systems: MPPCACD, SCLSTM, OCSVM, and IF. In the result of experiments, all methods shows the similar performance in true positive. As you can see in the last line in the table, all methods detect 2 anomalies out of 3. Whereas, ITAD clearly outperforms other methods in terms of false positive. Other methods produce a total of 9, 25, 18, and 18 false positives respectively, but ITAD reduces the total number of the false positives to 1. In satellite system, when a temporal glitch is detected from only one telemetry in a subsystem, as you can see in the figure above, it is highly likely that it is trivial outlier, not actual anomaly. ITAD does not report this kind of trivial outlier. Whereas, when a temporal glitch is in the multiple telemetries simultaneously, as shown in the figure below, actual anomaly is discovered. ITAD detects it as a true positive. This is reason why our ITAD reduced the false positives drastically and shows high performance. Thank you.